Okay, so in this video, we're going to be introducing sets, and we're going to be talking about some of the basic definitions of sets that we should be familiar with. So this is just to bring us up to speed and remind us of some of the definitions that we previously have done involving sets. So on slide 3, we begin here by talking a little bit about what a set is. The word set and element are undefined terms of set theory, just as a sentence, true and false, are undefined terms. So this definition here is very, very hard to properly define. So what we are going to be focusing on in this section is not so much the definitions, but rather how to use some of the various properties of proofs. So, sorry, of sets. So we begin with our first one here, and this definition here, sorry, this notation is called the subset notation. So this reads that A is a subset of B if and only if, for all x, if x is an element of A, or it's sometimes read as x runs through A, or if x belongs to A, then x is also an element of B, right? And this here is the negation of the statement, which is that x is inside A, but we see that x is not inside B. We also have the notation here of a proper subset of B. So A is a proper subset of B if and only if it's a subset. That's number one. And number two is that there is at least one element in B that is not in A. So here are some examples. So we have two sets here, A and B. Is A a subset of B? Now, A has the element, or rather this is called a singleton, okay, because it's only one element. It wasn't defined before, but this is called a singleton, and it's only one element here. A only has one element, namely the symbol 1. So this element is also one of the elements in B, which is this one here. Notice that for it to be inside B, it also has to have these curly braces as well. So B has 1, that is the element 1, and it also has this singleton 1 in it, right? And the singleton 1 is this one here. So that's why we can say A is a subset of B. If so, is A a proper subset of B? So this is where it's different. So since 1 is not the same thing, it's not equal to the singleton 1 or the set that contains 1. This here is the number 1, that is the value of 1. This here is the singleton 1, is the set containing the set containing 1, right? So the set 1 is not an element of A, and so there is an element of B that is not an element of A. Hence A is a proper subset of B because it has at least 1. So now we reach to proofs, okay? So this here is our first and one of the most basic definitions in set theory here. To prove that X is a subset of Y, or that A is a subset of B. Same thing. The intuition behind this proof is that in order to show that one is a subset of the other, all we have to do is take an element, assume that the element is inside 1, let's say X is inside, well, small x is inside the first set X here, and then somehow show that that element is also inside Y. If we can do that, then we have shown that one is a subset of the other. Of course, the formal writing of this proof is much longer. Okay, so here's a brief outline of how this would look. So suppose X is a particular, but arbitrarily chosen element of A. So in this case of X. And then somehow these 3 dots here means we have to go through a series of steps in order to conclude that X is also an element of B. Okay, so that is the intuition behind these proofs here. Okay, and here are some examples here for you to go through on your own time. Now we reach to set equality. So what does it mean for two sets to be equal? So in order for me to say that two sets A and B are equal, so this happens if and only if A is a subset of B and B is a subset of A. So if I were, or if I was asked to prove that A is equal to B, then I would have to show that an element X, right, or small a or whatever is inside this set, then somehow show that that's also inside this set, and then do the same for this here, and choose maybe a different element or the same one. Okay, and then we have to show for both cases, because it says if and only if this happens and this happens. So therefore we must show that that element is in here and also inside here, and similarly for this. This version of the definition of equality implies the following: to know that a set A is equal to a set B, you must know that both A is a subset of B and B is a subset of A. Here is an example to prove that is A equal to B? Yes, right? So this here is an example for you to read to show that so we prove first that A is a subset of B, then we prove that B is a subset of A. Okay, so now that we have established some of the notation here inside sets, let's talk a little bit about Venn diagrams. Please note, for this course, drawing a Venn diagram is not a proof, right? It's not a proof. It may help to illustrate your proof, but it does not constitute a proof itself, like a formal proof. Okay, except in the cases where you are asked to draw a Venn diagram in order to show your proof, right? And if you look at some of the later tutorial sheets, you will see that there are some questions like this. So if A and B are sets, right, represented as regions in the plane, then the relationship between them can be visualized as follows here, right? So this shows that A is a subset of B here because there are some elements in A, if we can show it, right? Let X is inside A or something, and then it's also inside B. So we can write like this. These here show that A is not a subset of B. Note that when we spoke earlier about, or we haven't reached it yet, union and intersection of sets, right? We will see that A intersect B in this case, if they have an element in common, is not equal to something called the empty set, right? And this can be included in this section here. That will become important when showing that sets are pairwise disjoint or otherwise. Here's an example of some of the relations among sets of numbers for your self-reading. And we now reach operations on sets. Okay, so we reach here to something that is called a universal set, or a universe of discourse for the discussion. So the first one that we have here is the union of A and B, denoted by A with this big U sign. It's called a union. B is a set of all elements that are in at least one of A or B. At least one. However, for the intersection of A and B with this N, it is a set of all elements that are common in both A and B. All of the elements for the intersection, however, for the union, at least one, right? So that is the difference between them. Number 3 is the difference of B. So the difference between some two sets denoted by B minus A is a set of all elements that are in B and not in A. The complement of a set is denoted by A with a C here. So we will utilize this notation here for this course. Sometimes you may see A with a dash on top, right? In some classical books, you may see A with a solid line that is placed on top, which we will not be using. We'll just use the C here for complement. Also note that sometimes we can denote the complement as U, where U is the universal set, minus A, and that is also the complement. But that notation is used here for difference of a set, but it can also be used for complement. However, we will keep the definitions as they are stated here, and we will use these going forward just for simplicity, right? So for symbolically, A union B is equal to X, that is inside U. U is a universal set. X is inside A, or X is inside B, because remember I said at least one, so we only need one element. Or for the intersection, it's all the elements, so that's why we have and. For the difference, we have X is inside one of them, but X is not inside the other. And for the complement, it's X is inside universal set, such that X is not inside A. So the complement of A is all the elements that are not inside the element, not inside the set A, right? So here are some Venn diagrams that represent union, intersection, complement, and difference. So these are union here. It's at least one. Intersection is all the elements. Shaded region over here represents the difference, sorry. And this one here is the complement. It's all the elements that are not inside A. Similarly, for if I had B complement, it would be all the elements that are not inside B. So here are some examples. So suppose that we have a universal set from A to G, and A, B are these sets here. Then what is the union, intersection, difference, and complement? Well, the union will be everything. It will be A, C, E, G, A, C, E, G, D, E, F, G, D, E, F, G. The intersection here now will be the elements that are in A that are also in B, right? So what are the elements in A that are also in B? So we have A here, we don't have a A. We have a C here, we don't have a C. We do have an E here and an E here. So that's how we put E. And we also have a G here and a G here. So that's how we put G. The difference between these sets over here now, all the elements that are in here but not inside here. So we have D and we have F, because we don't have a D and F here. So that's how we write this. And the complement here of A are all the elements of A, all the elements, sorry, that are not in A. So I have A, C, E, and G over here. So I can't put A, C, E, and G. I have to put everything else. So that's D. That's D. I have to put B. So I put B, and I have to put F. Okay. This here on slide 32 gives the operations on sets. Okay, this open brackets here, open parentheses, is the open set A comma B, and it's denoted by this over here. X is inside the real numbers, such that X is restricted between A and B. If we have a half open interval here, so it's open on A, but it's closed on B, so we call it half open, right? Then we have X is restricted like this. It's equal to here because it's closed. Okay, so if it's closed on both ends, then both of the inequalities will be equal as well, and wherever it's closed, it will be equal here. We also have a set here A comma infinity, so it will be all the elements starting from A all the way to infinity. That's how we have X greater than A. right? Because it's all the elements. And similarly, the understanding for this will also be applied to here. Wherever it's restricted, we'll have a equal sign. These here are some examples of the number line that we have known previously. So it's just included here for your reading. These notations here are just an extension of what we spoke about earlier with union and intersection, but in a general sense for large sets. So for the union here, this talks about some set here A, starting from I equal to 0. So we'll start at A0 all the way to n, whatever n is, right? N could be 5, 7, some number. Right, so it's restricted to a number here. However, over here in the second one for this union, it's going on till infinity. So it's for at least one non-negative integer I. And similarly for the intersection as well, it's a large intersection of all the elements x is inside A for all I equal from 0, because we start here at 0 to n. This is an alternative notation, which is quite cumbersome because we have to keep rewriting A0, A1, etc. This is much easier to write. And here are some examples of finding union and intersection. Now we reach to a special type of set that's called the empty set or the null set. So we have stated that a set is defined by the elements that compose it. So this being so, can there be a set that has no elements? Well, yes, right? Because it is a very unique set, and we call it the empty set or the null set. And we denote it by this symbol, like a 0 with a slash that comes between it. So what is the intersection of these two sets, 1, 3, and 2, 4? Well, there are no elements here that are inside here. So they have no elements in common. So they are both equal to the empty set because they have no elements that are in common with each other, right? So this example here asks to describe the set D, where x is restricted between 3 and 2. So since they have no numbers here that satisfy this inequality, D has no elements and D is equal to the empty set. Okay. So when I spoke earlier about the two sets in the Venn diagram, and I spoke about that it's pairwise, disjoint, and so on. Now we come to disjoint sets. Two sets are called disjoint if and only if they have no elements in common. So remember that the two Venn diagrams were separate as they were here. So what that Venn diagram was telling me that these two sets here, A and B, have no elements in common with each other. So these sets here, A and B, will be a Venn diagram of two sets that are disjoint. And symbolically, we write it as this: A intersect B is equal to the empty set. And visually, if we go back to the previous slide, which we were just on, we would see that that is how it would look. So A and B are disjoint if and only if the intersection is equal to the empty set. Are these two sets here disjoint? Yes, because this has 1, 3, 5, this has 2, 4, 6. Once again, they have no elements in common with each other. So this is equal to the empty set. So this brings us to this definition here. Some sets A2, A1, A2, A3, going down all the way maybe to AN, are mutually disjoint or pairwise disjoint or non-overlapping if and only if no two sets AI and AJ with distinct subscripts, so they can never be the same set, have any elements in common. So AI intersect AJ will be equal to the empty set whenever I is not equal to j. So suppose that this was a1 and this was a2, then this would be an example of that, because this would be like ai and aj. They are different, they have no elements in common, and they are equal to the empty set. Here are some examples of mutually disjoint sets. And then we have a small part here, small section on the partition of a set. We forgot, or it was excluded, to mention one thing about the empty set here in the previous section, which is that the empty set is a subset of every set. And in fact, we can even say that every set is a subset of itself. In fact, we can actually show that this is true. So let's actually let's show that the empty set is actually a subset of every set. So in order to show this, let's begin here by writing I want to show, suppose that we have a set S. So suppose that S is a set. Okay, then I'm saying that, well, two things happen actually. Number one is that the empty set is a subset of S. And the other thing is that the set is a subset of itself, which is obvious. So we can write trivial, right? But the first one here, this is interesting to us because, so we can write proof. Okay, so we can begin our proof by identifying each part of this statement here. So we can say let S be a set. That was kind of given. So we have to show that somehow the empty set is a subset of S. So in other words, what we really have to show is that for all S, or let's use X instead, for all X, right? So X is our element. X, the element, is inside the empty set, and this implies that somehow X is also inside S, is true, right? Why? Because the empty set has no elements. But we could say because the empty set contains no elements. Okay, so if the empty set contains no elements, then this follows that my claim here that X is inside the empty set will always be wrong. So is always false. So the statement now, okay, so let's get another page. So we can say it follows that the statement which I have written, the statement X is inside the empty set, sorry, X is inside the empty set, somehow implies that X is inside S, is always true. Is always true, right? Why? Because the hypothesis that it is always false and a conditional statement but a false hypothesis will always be true. So therefore, for all x, if x is inside the empty set, somehow implies that x is inside S, then that will be true, right? So if we can write this formally, it will be so since this is always true, we can say because its hypothesis is always false, and a conditional statement with a false hypothesis is true. Therefore, let's call this something. We can call this equation 1. Therefore, 1 is true. Right? And this completes the proof. Right? And of course, the second one, S is a subset of S. This is left as an exercise. Okay, it's very trivial to prove. Okay, so this is the only thing that we forgot, or was left out rather, of this part of the empty set section. So now we are back to partitions of sets. Okay, so partitions of sets in this sense is very easy to understand. Okay, it's just a set with some elements and we put them like this, but the continuation of this will be done in a later section when we reach something called equivalence relations, right? Partitions of sets and equivalence relations are intertwined. Okay, so for this one, we'll just loosely define a finite or infinite collection of non-empty sets is a partition of a set A if and only if, number 1, it's the union of all the AIs, and 2, the sets are mutually disjoint. Let's go back and remind ourselves what are mutually disjoint. Remember, when we say mutually disjoint, we also mean pairwise disjoint, right? It's the same thing, which means that the intersection is equal to the empty set. And here are some examples. Let A and A1 and A2 and A3, is this a partition of A? Yes, it is. Because if you look at the elements of these sets, we have 1, 2 here, we have 1, 2, 3, 4, 3, 4, 5, 6, 5, 6. Is it a partition yet? Yes, it is. So if I were to draw this, excluding the A4, of course, and this entire region was A3, then we would see that A makes up A1, A2, A3. So yes, it is. Right? And similarly for the second example, which you can look at, it's also the same. Now we reach to one of our last subsections, which is the power set. So there are various situations in which it is useful to consider the set of all subsets of a particular set, right? And that is the power set. So this power set, okay, so it says that given a set A, the power set, so we have this fancy P, is the set of all subsets of A. So in fact, if we go back to this definition here, and we see this is a subset of A, this is also a subset of A, this is also a subset of A, then we can write this here, this partition, as the power set, right? But how do we write it? So find the power set of the set XY. That is, find fancy P of XY. So we have the set now containing the set called XY. So the power set is a set of all subsets, which is why I did the proof before, which shows that the empty set is a subset of every set, which was left out. Okay, which is why this proof is very important. The empty set is a subset of every set. So when we write our power set, we need to always include the empty set. So also any set is a subset of itself, which is why we had S as a subset of S as before, which is a trivial proof. So XY is inside the power set itself. The only other subset of XY are the singleton X and the singleton Y. So then we take all the elements and we write it in terms of the power set. So the power set has the empty set. It also has the singleton X, that's this one. It also has the singleton Y, that's this one. And it also has the set contained in the set itself, which is the set of X, comma, Y. So this is how we would write the power set. We can even do an extra example here to further illustrate our point here of the power set. Let's just do one example to talk about the power set. So suppose I had a question which says, question, what is the power set of this set? Let's write this set so we know that it's a set of something. Let's do 0, 1, 2. What is the power set of 0, 1, 2? The power set will be fancy P. I can't draw the fancy P, so I'll put something like this. So we put regular parentheses. Then we have our curly braces 0, 1, 2. This is equal to, so let's start with what we know. We know the empty set is a subset of every set. What else do we know? We take each element here by itself. So we start with the singleton 0, comma, the singleton 1, comma, the singleton 2, comma. Then we also do them in pairs because now we have 3 elements. So we have to do 0, 1. So all the possible combinations. So we have 0, 1. That's inside there. What about 0, 2? We have 0, 2. What else do we have? We have 1, 2. So comma 1, 2. And we have any possible combinations again? No, except the set itself. So comma 0, 1, 2. Close brackets. Right? So this is the power set of this. What about so we just spoke about the empty set here is always a subset of any set. So a nice question to ask would be, so a nice question to ask ourselves would be, what is the power set of the empty set? So what is the power set of the empty set? Is it possible to find something like this? What is the power set of the empty set? So in other words, I'm asking, so I'm really asking, what is the power set of this set here? It is the set of this. What is the power set of this? Now, the empty set has how many subsets? The empty set has exactly one subset. What is that subset? It is itself. So we can say that the empty set has exactly one subset, i.e. itself. So if this statement is true, and it is true, then the power set, so let's go fancy P of this will just be equal to this. But then we have to ask ourselves, well, how many subsets are there inside the set of the empty set? So this set with the empty set inside has 2 subsets. Is that true? Yeah, yes, that is true. What are the 2 subsets? It is just like before, where we had 1, 2. We have the empty set and the set containing the empty set itself. So we have the set, this has exactly 2 subsets. That is phi and itself, and the set of the set itself, which is the set containing it. Right? So therefore, now we can write what is actually the power, fancy P, the power set of, now we write the parentheses, curly braces. What is the power set of the empty set? It is the empty set, comma, and the set containing the empty set itself, close braces. Right? So what does this tell me here? If I recognize a trend between this example, this one, and what we have done before here, we see that if a set has, let's call it n amount of elements, right? So this one has maybe 4. All right, so if a set has n elements, then the power set has 2 to the power of n elements, right? So this has 2 inside here, so 2 to the power of 2 is how much? 4. Didn't we have 4 elements here? 1, 2, 3, 4. So this is true, right? Similarly with this one here, this has 1 element here. This is 2 to the power of 1. So I expect to get 2 elements, and I did get 2 elements right here and right here. So this theorem here, or this result, or this observation is always true, right? So if a set has n elements, then the power set has 2 to the power of n elements. Okay, so now that we have that, let's go back to where we left off. And we have reached the Cartesian product here. Okay, so given some sets a1 to an, the Cartesian product of a1 to an is denoted by a1 multiplied by a2 multiplied by all the way down to an, and is the set of all n tuples, right, from a1 to an, where a1 is inside this set and a2 is inside this set, etc. Symbolically, we write it as this here. So here are some examples. So what is the Cartesian product of xy multiplied by 1, well, another set, 1, 2, 3. So it's x multiplied by 1, which is x comma 1, x multiplied by 2, x comma 2. Similarly, x multiplied by 3, x comma 3, and you do the same thing for y. So it's like multiplying sets, right, in an ordered way, right? And we can see that it must be done in an ordered way when we look at b, right, which is also for your reading. From slide 64 onwards, this is just for your further knowledge. If you wish to look at it, it is just an algorithm to check whether one set is a subset of the other. So in your own time, when you fetch your notes from online, then you can read this, and if you are interested in it. Okay, so this is the end of this first section of chapter 6, right? It's just to introduce some of the terms, such as what is a subset, what it means for two sets to be equal, what is the power set, the empty set, which is important, and how do we use these facts to prove some theory involving set theory. So in the next section, we'll be using all of this to prove some very interesting results in set theory.